What if the oldest light in the universe is still reaching you right now? Not light from a distant star, not light from a galaxy billions of light years away. Something older, something that began its journey when the universe itself was still incredibly young. Every time we look into the night sky, we are looking into the past. But there is a limit to how far ordinary light can take us. Long before the first stars ignited, before galaxies assembled, and before planets existed, the universe was a very different place. It was hot, it was dense, and it was filled with a glowing mixture of matter and radiation. There were no familiar stars scattered across the darkness because there was not yet a darkness like the one we know today. The universe was filled with an extremely hot plasma in which charged particles constantly interacted with light. Photons were everywhere, but they could not simply travel across the universe. Imagine trying to see through a thick fog, except the fog is made of the fundamental particles filling the entire cosmos. A photon could move for a short distance, collide or scatter, and change direction again and again. Light existed, but the universe was opaque. For hundreds of thousands of years, this cosmic fog remained. And then something changed. As the universe expanded, it cooled. The temperature gradually fell, and the conditions became calm enough for electrons to become bound to atomic nuclei. Neutral atoms could finally form. This transition changed the universe in a profound way. The fog began to disappear. Photons that had previously been scattered over and over could suddenly travel enormous distances without being constantly interrupted. In a sense, the universe opened its curtains for the first time. This happened roughly 380,000 years after the Big Bang, and the light released during that transition has been traveling ever since. Today, we detect that ancient radiation as the cosmic microwave background, or CMB. It is one of the most remarkable things humans have ever observed. The light has stretched as the universe expanded, losing energy and shifting into the microwave portion of the electromagnetic spectrum. Yet its origin remains incredibly ancient. When scientists map this radiation across the sky, they find something extraordinary. The universe was almost perfectly uniform. Almost. That small word contains one of the greatest stories in modern cosmology. Across the young universe were tiny differences in temperature and density. They were extraordinarily small, but they mattered. Because gravity does not treat every region of space equally. A region that contains just a little more matter than its surroundings has slightly stronger gravitational attraction. Over enormous periods of time, that difference can grow. Matter falls toward denser regions. Those regions become denser still. And eventually, the nearly smooth young universe begins to develop structure. The great cosmic architecture we see today did not appear all at once. It emerged gradually. Tiny primordial fluctuations became the seeds from which larger structures could grow. Gravity gathered gas and dark matter into increasingly concentrated regions. Clouds formed. The first stars eventually ignited. Those first stars were surrounded by a universe that was still young, dark, and radically different from the cosmos we see today. But their light began to transform their surroundings. The first galaxies assembled from stars, gas, and dark matter. More galaxies appeared. Groups and clusters grew. Enormous filaments of matter stretched across space, connecting dense regions while vast cosmic voids opened between them. Over billions of years, gravity turned tiny differences in the early universe into the enormous cosmic web we observe today. When we look at that web now, it is difficult to imagine how small its beginnings were. The largest structures in the universe carry a memory of the smallest variations in the young cosmos. And this is where the ancient light becomes more than a distant signal. It becomes evidence. The cosmic microwave background gives scientists a remarkably early view of the universe. It allows researchers to measure subtle variations across the sky and compare them with predictions from cosmological models. Those patterns contain information about the conditions of the young universe. They help scientists study the distribution of matter, the geometry and expansion of the universe, and the processes that shaped cosmic structure. But there is an important distinction. The CMB is not a photograph of the exact first instant of the universe. It comes from a much later period, when the universe had cooled enough to become transparent. What lies earlier than that is harder to observe directly with light. Before the universe became transparent, photons could not travel freely across cosmic distances. The early universe was opaque to electromagnetic radiation. That means the CMB acts as an observational boundary for ordinary light. It takes us astonishingly close to the early universe, but it does not show us everything. And this boundary raises an even deeper question. What happened before the ancient photons began their journey? One possibility discussed in modern cosmology is cosmic inflation, a theoretical period of extremely rapid expansion in the very early universe. In these models, tiny quantum fluctuations could have been stretched to enormous scales, eventually becoming related to the primordial variations from which cosmic structure grew. But inflation is not something we simply photograph. It is a theoretical framework whose consequences can be tested through observations. That distinction matters. Science becomes powerful not by pretending that every mystery has already been solved, but by carefully separating what we observe from what we infer. And the CMB is powerful precisely because it allows that process. We measure patterns, we compare them with physical models, we test predictions, and from those comparisons, we build a picture of cosmic history. The deeper we look, the more remarkable the connection becomes. A tiny variation in the young universe can be connected, through gravity and time, to a galaxy. A galaxy can become part of a cluster. Clusters can lie along enormous filaments, and those filaments form part of the cosmic web spanning billions of light years. The universe we see today is therefore connected to conditions that existed when it was unimaginably young. There is a kind of cosmic continuity running through the entire story. The ancient radiation did not stop existing when the first stars appeared. It continued traveling. It passed through an evolving universe. Stars were born and died. Galaxies assembled and merged. Clusters grew. The cosmic web became more complex. And still, those ancient photons continued their journey. For billions of years, they traveled through expanding space. The wavelength of that radiation stretched along with the expansion of the universe. What began as much more energetic radiation eventually became the faint microwave background that instruments can detect today. And that means the sky is carrying an ancient message, not a message written in words, not a message from an observer who stood outside the universe. A physical record, a pattern left behind by the conditions of a very young cosmos. When we study it, we are not simply looking at something far away. We are looking backward in time. The farther the light has traveled, the older the information it carries can be. And the cosmic microwave background takes us farther back than ordinary stars and galaxies can. It gives us a view of a universe before the first stars existed, a universe before the Milky Way took its present form, a universe before Earth, before the sun, before planets, before life. The radiation was already there, and today it is still arriving from every direction. That may be the most astonishing part of the story. The oldest light is not locked away in the distant past. It is still part of our observable universe. Ancient photons are still reaching us. They pass through the space around our planet. They arrive at detectors built by human beings. And within their faint variations is information about a universe that existed long before there was anyone here to see it. For most of human history, the universe was something we could only observe from the narrow window provided by our eyes and telescopes. But the cosmic microwave background changed that perspective. It allowed us to detect the afterglow of an early cosmic epoch and use it as a tool for reconstructing the history of everything that came later, from tiny fluctuations to stars, from stars to galaxies, from galaxies to clusters, from clusters to the cosmic web. And behind all of it, a nearly uniform ancient radiation field that has been traveling across the expanding universe for billions of years. The story begins with something almost impossibly small, a tiny difference. A slight variation, almost nothing. And yet, through gravity and time, those small differences became structure on a scale almost impossible to comprehend. That is one of the deepest lessons written into the oldest light. The universe we see today was not separate from its ancient past. It grew from it. Every galaxy, every cluster, every filament, and every vast cosmic void belongs to a history that reaches back to the young universe. And when we look at the cosmic microwave background, we are seeing one of the earliest chapters of that history, not the beginning itself, but close enough to glimpse a universe before the familiar universe had taken shape. A universe without stars, a universe without galaxies, a universe filled with hot plasma, slowly cooling as space expanded. Then, suddenly, by cosmic standards, the fog cleared. Light began to travel freely, and that light never stopped. It crossed an expanding cosmos for billions of years until, eventually, some of those ancient photons arrived here, at Earth, at our instruments, at our moment in time. So the next time you look into the night sky, remember that the universe is not simply showing you distant objects. It is showing you history. And beyond the stars and galaxies, surrounding us in every direction, there is an even older signal, a faint remnant of a universe that was once young, hot, dense, and almost perfectly smooth. The oldest light is still here, still traveling, still reaching us, and still carrying a memory of the universe long before the first stars ever shone.